Now I'd like to do an example from section 4.2 and 4.3, just a general example of using these techniques that we learned about to at least partially analyze a function, find critical numbers, find intervals of increase and decrease, etc. So to find the critical numbers, remember that we find where the derivative f prime is 0 or undefined. Now in this case, the function we're working with, f of x, is a polynomial, and polynomials are defined everywhere, their derivatives are defined everywhere, so we won't have any places where the derivative is undefined, but we can certainly look for where that derivative equals 0. So Cn stands for critical number, so to find the critical numbers, we're going to first take the derivative, 4x cubed minus 4x. We're going to set that derivative equal to 0. In this case, we can factor a 4x out of each term. And then we're going to set each factor to 0. So just some basic algebra here. So we get that x equals 0 and x equals plus and minus 1 when we solve that. So these are the critical numbers. Now remember that critical numbers have to be in the domain of the function, but again, polynomial functions are defined everywhere. Their domain is always all real numbers, so we won't have any issue with values that are not in the domain. But in general, to be a critical number, that value has to be in the domain of the function. Okay, so to find the intervals of increase and decrease, what we want to do is check the signs, SIGNS, of f prime. I'm going to say around the critical points or critical numbers. So I'm going to set up a number line. So let me I should have numbered these, I guess. I'll call that 1. I'll call this 2. So I'm going to use the first derivative test, basically, which is really to test to see if I've found maxes or mins, but it also finds automatically the intervals of increase and decrease. So what I do is I set up a number line and I put the critical numbers on there, and then I look at the top of the number line for the sign of f prime, and I look at the bottom of the number line for the behavior of f. So I take a number to the left of -1, for example, -2, and I plug that into f prime. So I don't actually care what the number itself is. All I care about is what the sign is, whether it's positive or negative. Now, depending on the function, the one we're doing here is fairly simple and straightforward, so it might be easy enough to just plug the number in and you can tell what the sign's going to be. You can use your calculator to do this as well. If you have f prime in your y equals and you go to the table and you let x be, for example, -2 or -3 or -5 or -10, anything to the left of -1. In that case, in this case, we will get a negative number if we find f prime of -2 or anything to the left of -1. Then we need to plug in a value in between -1 and 0. So for example, x equal -1/2. We want to plug that into f prime, right? So I don't want to write too much on this because it's going to get messy. But I plugged in f prime of -2 and I got a negative number. On this one, if I plug -1/2 into f prime, I get a positive number. Again, you can try this out and see. If I take a number in between 0 and 1, like 1/2, you could use 3/4, you could use 0.1, any value in between 0 and 1 is fine. In this case, when I do that, I get a negative number. And then if I pick something bigger than 1, again, I would probably do 2, but just for variety, I'll try 3. You could do 5, 10, 15. Anything bigger than 1 is fine. You could do 1.1 if you want. I plug that into f prime. and I actually look at the factored form, and it's easy to tell what the sign's going to be. In this case, it'll be positive. So again, that can be done in the home screen of your calculator. It can be done in the table if you have the derivative plugged in to your y equals. What you want to make sure happens is that you are plugging those x values into f prime and not into f or any other function. It's got to be f prime. All right, now again, just because this is going to get too crowded, I'm going to take this out. And what these signs of f prime tell me about f are its behavior. So for example, if f prime is negative, f is decreasing. If f prime is positive, f is increasing. If f prime is negative, f is decreasing. And if f prime is positive, f is increasing. So I can say f is decreasing on the interval from negative infinity to negative 1, and the interval from 0 to 1. So notice these are not ordered pairs. These are intervals, and they're not closed. Well, of course, any interval with infinity does not have a closed bracket. But these are open because at those critical numbers, the function is neither increasing nor decreasing in this case. So we have to keep those intervals open. F is increasing on the interval from negative 1 to 0, and on the interval from 1 to infinity. So keep in mind, how do we know that these are the only intervals we need to consider? What if there's some other value to the right of x equal 1 where f prime changes sign? If that were true, then when we set f prime equal to 0, we would have found more roots. So we don't have to worry about that. Okay, now part 3, find local max and min values. Well, so I can see by the way my arrows go, when my function goes from decreasing to increasing, that creates a min. When my function goes from increasing to decreasing, that creates a max. So I'm making a note on my number line, but I'm going to make some statements here. So f, now this is about f, has a local minimum at, that's an important word, x equal negative 1 and x equal 1. And I can also say f of x has a relative or local maximum at x equals 0. Now the question said find the local maximum and minimum values. Okay, so the minimum values are y values. So that would be f of negative 1, which in this case happens to be equal to f of positive 1, and that is 2. And again, how do I know that? Because I plugged those x values into the formula for f, and you can do the same. And the maximum value is, okay, so I'm saying what the max and min are as opposed to where they are at. So the maximum value is f of 0, which is 3. Okay, then part 4, find intervals of concavity and inflection points. So for that, right, we want to find where f double prime equals 0 or is undefined, and then again we're going to have to test by checking signs. So let's see what that means. Now I'm going to find f double prime of x, so I'm taking the derivative of f prime. That'd be 12x squared minus 4. Again, because this is a polynomial, the second derivative will be defined everywhere. That's one of the nice properties of polynomials. They're everywhere continuous, differentiable, all their derivatives are everywhere continuous, no sharp corners or cusps or asymptotes or anything like that. Okay, so I'm going to take this second derivative and set it equal to 0. And from that, I get that x is plus or minus 1 over the square root of 3 when I solve that equation. And again, what I have to do is set up a number line, and I'm going to put each of these values on the number line, and then I'm going to check the sign of f double prime, and that's going to tell me about the concavity of f. So when I plug a value for x less than negative 1 over root 3, and again, if you're not sure what number that is, you can put it in your calculator to get a decimal, or you could just take something that's, you know, definitely is very safe, like negative 10 or negative 5 or something like that. And when you plug that into the second derivative, you get a positive value. In between negative 1 over root 3 and positive 1 over 3 is one of our favorites, x equals 0. That's always fun to plug in because it simplifies so easily. So in this case, f double prime of 0 is negative 4. So that's negative. Again, I don't really care about the number, just the sign. And then when I plug an x value bigger than 1 over root 3, I get, once again, a positive value on the second derivative. So again, make sure you're plugging these values into the correct function. We are plugging into f double prime. Now, what does that tell us about f? It tells us the concavity. So when the second derivative is positive, f is concave up. When the second derivative is negative, f is concave down. So again, I can answer the question, f is concave up on the interval from negative infinity to negative 1 over root 3, and from 1 over root 3 to infinity. And f is concave down on the interval from negative 1 over root 3 to 1 over root 3. All right. Now, we're also supposed to find inflection points. So if the function f changes its concavity, whoops, I was about to write concavity there, then it's got an inflection point. So if the second derivative actually changes its sign, that means we have an inflection point. Now, the question said, find inflection points. So there we really should give ordered pairs. So the inflection points of f of x are negative 1 over root 3, and then again, if you plug that into f of x to get the y corresponding y value to be 22 over 9, and then the other inflection point is at positive 1 over root 3, and again, if you plug that into f, the original function, you'll get a y value of 22 over 9. So keep in mind, you have to just watch for which function you're plugging x values into depending on what it is you're trying to accomplish. Sometimes you're plugging into f, sometimes you're plugging into f prime, sometimes you're plugging into f double prime. So you just have to be aware of which thing it is you're trying to find that will get you what you need. Okay, then we're supposed to sketch the graph of f of x. Now, one of the nice things about doing all this analysis before we put the function in our calculator is it can give us an idea of a good window. So, for example, let's see. Oh, it made me a duplicate, darn it. Oh, I could just continue down here. Okay, so sketch the graph. What is that up to? Number 5. I mean, I have a basic idea of the function's behavior, and I'll do more than one sketch based on where my critical numbers were and my increasing, decreasing. I have a function that decrease, increase, decrease, increase. So this is the basic shape. Okay, and then I know what the x coordinates are and the y coordinates of these spots. So for example, this is a point, according to what I did earlier. minimum value, that's negative 1, 2. And this is a point at positive 1, 2. And this is a point at 0, 3. So knowing that can help me actually come up with a decent window. So for example, I might try, if I were using my graphing calculator, because you can start with a standard window, but sometimes that actually doesn't work that well. But for example, I want to go a little to the left and right of these critical number x values, the leftmost min and the rightmost min there, so maybe 2 beyond that would be fine on the x. And then the y, I don't technically need to go below a y value of 2, but maybe to start at y equals 0. And then again, I have a relative maximum at a y value of 3, so I want to go a little bit beyond that. Maybe I'll go as high as 10. And you can try that, and if it doesn't look good, you can always adjust it. Okay, but then I can come up with a decent sketch. I know that the graph has the point at 0, 3. I know it's got a point at negative 1, 2, and a point at 1, 2, and it basically looks like this. Okay, again, not the greatest drawing, but not the worst one I've ever done either. And if you're going to use your graphing calculator, which you're welcome to do, you just want to make sure you pick a window that actually does a good job of showing the important behavior. So if your window, for example, is too zoomed out, you won't actually see the maxes and mins. It'll just look like a bucket shape. Okay, and then last but not least, number 6, determine whether any of the local extrema are global. So in this case, I can see that the points at negative 1, 2 and positive 1, 2 are global. They are the lowest points on this function. There is nothing lower. Can't talk and spell at the same time. These are global minimum points. So we could say the global minimum value is 2, the y value, right? So again, we have the locations of the minima. The minimum points occur at x equal 1 and x equal negative 1, but then we have the minimum is 2, right? And that at negative 1, 2 and positive 1, 2, those are the lowest points on the function overall. There's no points any lower than that, so those minimum are also not only local but global. Now, a function doesn't always have global extrema. It might not have any. And I wanted to mention before I close that when I worked these number lines for parts 2 and part 4, it did happen that once I got my first sign SIGN, then after that they alternated back and forth, plus minus, or minus plus minus plus. That doesn't always happen, so sometimes students put in the first sign, like the first negative value in part 2 there, and then they just fill in the other ones assuming they're going to reverse themselves. They don't always do that, so it's really important that you actually do plug values into the derivative and actually check what the sign is, because sometimes the sign does not change.